Hello, everybody. How are you guys doing today? So today we're going to be looking at looking at solving free fall problems. So we've talked about free fall here last week. We talked about how you know Galileo came about and looked at free fall, and we looked at the law of odd integers and all that kind of stuff. So now we're going to be looking at actually applying concepts of gravity and free fall to solve problems. So we're going to still be looking at the same equations that we've had with the equation sheet and all that. We're just going to be tweaking them some and applying and solving problems using guess. Okay, so the types of free fall problems that you will see, there's basically three types. We have one that's called a drop type of problem. We have one that's called a throwdown type of problem. And then we have one that's called a throw up. So I've kind of made these up. These are just a way that I think that will help students to understand how to maneuver and kind of identify different types of free fall problems. So just kind of keep that in mind, that it's not, these are not the official, I guess, especially the throw up. These are not officially labeled these. These are just my examples to help you with these problems. So again, we're using the same four kinematic equations, but notice what I did here. I changed them, and so instead of being v sub x, it's v sub y. Same thing for this. It's vy naught and ay. Again, instead of x equals, we have, this is y equals. Now remember, this one's not on your equation sheet, but I did add it to this slide. Okay, this one is on your equation sheet, but again, it's written with the x. And so when you solve these problems, remember, if they're free fall, if they're in the y direction, then instead of having x, you're going to put a y there. And then, of course, here's the last one. Vy squared equals vy naught squared plus 2ay y minus y naught. So now the thing with this is that with these equations, your a sub y, that is the acceleration in the y direction, which you can see up here, I say, of course, is gravity. And so anytime you have a free fall problem and you see a of y, or you see acceleration and you know it's a free fall problem, you automatically know that a of y is going to be gravity, and that's negative 9.8 meters per second squared. Okay, so with a drop problem, this is what we're looking at. So here we have a kid up on this rock, and he has a ball and he's dropping it. And you see that it falls. You can see that it also accelerates, right? It's close together, so it's falling quicker. And then, of course, it's spreading out. So you can actually just see like the motion of the ball here is showing you that it is accelerating. And then up here is our coordinates. So you can see, of course, in the y direction, it is falling. So here's what we know with the drop problem. And by the way, I will put these notes, because I have some notes, I believe, that I'll put these in the our folder for Google, our Google folder. And then if I remember to, I'll attach it to this week's modules. Okay. So anyways, so here we have Vy naught. That's going to be 0 because it's a drop problem. So that initially it's, you just let it go. The initial velocity is going to be 0. Because it's going down, you'll say that it's falling. So our y is going to be negative. Again, it's just going in the negative direction, so it's going to be negative. And Vy is the final velocity as it hits the ground. Okay, we know that it hits and it will come to a stop, but we want it as it hits the ground. Okay, so as it hits the ground, it's going to have some speed, some velocity. We want to know what that is. And that, of course, will be Vy, and it will be negative as well. And then a sub y is going to be gravity, right? And sometimes you can use g if you wanted to. And sometimes, too, you'll see that they even will round gravity to 10. Sometimes it's a little bit easier when you're doing some problems. You don't have to use a calculator sometimes if you make gravity 10. So that could be a possibility. And unless we are in the, if we're just doing some problems in the book and stuff, you can. Sometimes on your web, the Mastering Physics, they may say you can use 10. You just kind of have to be aware, because sometimes you have to put that in just right. Definitely in the lab, you'll have to make sure that you use 9.8 if we do any kind of lab where we have to find gravity. So But again, you can round to 10 sometimes on the AP test. All right, so then the next kind is called a throwdown problem, and it's just like a drop problem, except the initial velocity is not going to be zero. The initial velocity is going to be negative. So you can see here this guy is dropping, or excuse me, throwing something down. So the initial velocity, Vy naught, Vyo, is not going to be zero. It's going to be some number, like maybe 2, whatever. And whatever number it is, it's got to be negative because, again, it's going in the negative y direction. And then you can see that our y will be negative, the Vy as it hits the ground will be negative, and then again, gravity is negative 9.8. So the throwdown and the drop problems are very similar. Matter of fact, they're extremely similar. The only difference is that the initial velocity is 0 for a drop and not for a throwdown. All right, the last type of problem is a throw-up problem, and we actually kind of have 2 throw-up types of problems. The easiest one is what I'm going to kind of talk about first, and that's a symmetry type of problem, symmetrical. So with a throw-up problem, you can see that, like right here, right, that this is where it starts, it goes up, hits maximum height, and then comes back down. And notice that we're only looking at it when it leaves the guy's hand and it comes back to the guy's hand. So this is a nice and symmetrical type of problem. And being that symmetrical, that means that whatever's going on over here going up is also equal to whatever's going down. And I'll explain that here in just a second. So when you throw something up, the initial velocity going up is 0, and that's going to be right here where his hand is. So that is Vy naught. As it goes up, it's going to be losing speed because the motion is up, but gravity's pulling it down. So it's going to be decelerating. So as it goes up, it's going to slow down, slow down, slow down. And then when it reaches maximum height, the velocity is 0. It's going to stop for a brief second so it can come back down. But the acceleration at max height is not 0. The acceleration is still going to be gravity because gravity is still working on it. Gravity is still pulling it down. So at max height, gravity is going to be negative 9.8. And this is what a lot of students, I would write this down or make a note of it. This is where a lot of students have issues, is because they forget that. And so what they automatically say is at max height, they're like, oh, the velocity is 0, the gravity is 0. And that's not the case. Gravity is negative 9.8 all the time, because as soon as that object's released in the air, gravity is acting on it the entire time. So as it goes up, gravity's slowing it down, reaches a velocity of 0, changes direction. All right. And even because it's changing direction, right, it's accelerating. And then it starts to fall back down. And as it falls back down, it's accelerating. So going up, we have an initial velocity right here of 0. Going up, the y is 0. Coming down, our y will be negative. And then, of course, going down, the velocity will be negative. All right. Again, anytime anything's going up in that positive y direction, everything will be positive. And then if something's coming down in that negative direction, everything will be negative. Okay. So just a couple of things here then. Again, your Vy at maximum height up here is going to be 0. Remember I said it stopped. Okay, so going up, 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 your final velocity at the very top there is 0. And then when it comes back down, that initial velocity is 0. So it's kind of tricky because at maximum height, you kind of have 2 things going on. We have like the motion going up, and then you have the motion going down. And you kind of have to like divide it in half and kind of think about it when you're talking about these problems and doing these problems. You have to kind of focus on either the first part of it, so it going up, or looking at the second half when it's coming back down. And I talk a little bit about this in some example problems that I do, and also I'll mention it also in class. But again, at the max height, going up, your final velocity is 0. And then when it comes back down, that initial velocity, it's like a drop problem. It's like a throw-up problem to then a drop problem coming back down. All right. And then, of course, gravity is your A of y. And again, A of y is not 0 at max height, only the velocity. So again, looking at that symmetrical, and I might be repeating myself, but when you throw this object up, ball goes up, 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 and then it comes back down. So let's say it takes 2 seconds to go to maximum height where that velocity is 0. Then it also takes 2 seconds to come back down. So for a total hang time of 4 seconds. So going up is 2 seconds, coming down is 2 seconds for a total of 4 seconds. So sometimes they may ask you, what's the time to max height? And you would just say 2. And then they'll say, well, what's the total time the object's in the air? And then you would say 4. All right, so you can find time up and multiply by 2. You could find time down and multiply by 2. It's really up to you. And then, of course, because it's symmetrical, whatever velocity that you throw it up with, that's the velocity that's going to hit the ground with. So if I throw this ball up with a velocity of 5 meters per second, when it comes back to this position here, it's going to also be traveling at 5 meters per second, but in the negative direction. So it's symmetrical, you know. So if it's traveling, let's say at 2 meters per second here, it's 2 meters per second here in the opposite direction. So it's going to be negative 2 meters per second. So just keep in mind that it's like this because it's symmetrical. That's the key. Okay, now, what if it's not symmetrical? Okay, I call these gimpies, and it's, again, just my weird way of thinking about it. But here, you can kind of see the guy throws the ball up, and it comes back down, but it passes that initial position where it started and keeps on going. So the time up does not equal the time down. And so these are a little bit difficult because what you have to do is kind of separate it. You're going to have to kind of draw like a line down the middle, and you have to kind of analyze the going up part. Then you're going to have to analyze the going down part. The nice thing about the going up part is, again, similar to a normal throw-up problem, is when it's reached a maximum height, that final velocity is 0. And then as it starts to fall back down, that initial velocity is 0. So again, when you're looking at these throw-up problems, you have to think about it in terms of dividing it in half, and that going up, it's going to be positive direction, and then the second part coming down is going to be in the negative direction. But in both cases, at max height, right up here, the final velocity is 0, and then coming back down, the initial velocity is 0. So like I said, these are non-symmetrical or not symmetrical throw-up problems, okay? So these are what I call gimpy problems. This is just my weird twist on things. Okay, so just some reminders. Velocity and acceleration are not always in the same direction. However, acceleration acts down. Always, okay? Acceleration always acts down. So like going up, the velocity will be positive, the acceleration's negative. Coming back down, the acceleration would be negative, and so would that velocity. Remember that at max height, your acceleration is not 0. Only, it's always going to, only the velocity. All right, gravity will always be acting on the object. Free fall is uniform acceleration. All right, so that means that it's accelerating at 9.8 meters per second every second. All right, that's uniform acceleration. Again, may have symmetrical or non-symmetrical throw-up problems. And make sure you remember the difference between those. Okay. All right, so I have a video that I have attached or put in our modules, and the video kind of has me going through examples of throw-up problems, drop problems, and also throwdowns. So I've done 3 different examples for you to kind of help you with your online homework. And so make sure that you guys watch those videos or watch that example videos that I put up. And then the last thing is just some misconceptions. It's a video that I'm going to show you guys here, and it just kind of talks about misconceptions that people have about falling objects. So I'm going to have you guys watch this. And there we go. Maybe I won't. I am having technical difficulty. There we go. Sorry about that, guys.
Both falls above his head, and then he drops them at exactly the same time. What do you expect to see? Well, they're going to hit the ground at the same time. I expect them to both land at the same time.
Same time.
Same time.
Well,
I think they both will.
This one to hit the ground first. However, they would actually both hit the ground at the same time.
Why is that?
Science.
Yeah, science.
Now, the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed. From this height, yeah, pretty much. Just a constant speed all the way down.
Speed? Yeah, I think it'll be the same constant speed.
I think it's constant.
I seem to remember it being constant. I did decently in physics, and I seem to remember that's the answer.
Whereas the truth is, the speed of both balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar in terms of gravitational pull. They're both at the same and they'll fall at the same rate. I'm not like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull and you've told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is heavier and has more gravitational pull. But when I drop them, then they get equal with gravitational pull somehow.
Don't you think it's going to be like 5 times as much?
Yeah, you think, but it's not.
The way you're asking it, yes, but scientifically speaking, no.
The gravitational force on both these balls are the same.
Okay.
The gravitational force on both of these balls is the same.
Is that what you actually believe?
No, but it is.
Tell me what you believe.
I believe it should be more on this, simply for the fact that this is heavier. And just intuition tells me that it should be more. But after learning physics, we learned that it is actually the same.
I actually think the force on this ball is more than the force on this ball.
No, you don't.
I swear. I am not trying to mess with you. So,
Like in real life?
in real life and in physics, I will tell you that the force on this ball is more. All right, ready? 3, 2, 1.
Yep, see?
Same time.
Same times. I would say the force on the medicine ball is like a lot more because it's got a lot more weight, it's got a lot more mass.
Yeah.
But it's got a lot more inertia.
Yeah. Oh.
You guys remember that, right? It's got a lot of resistance to acceleration, so it takes more force to get it accelerating at the same rate as this ball. And that's why they accelerate at the same rate. Thank you guys so much for playing along. I appreciate that.
Sorry,
Thanks,
Derek.
Jess. That's all right.
Okay. So,
You're the guy.
all right. So that it is. There it is. And we will talk more about acceleration and free fall next time. Have a great day.